Hi, welcome to es301 Engineering Analysis. This is chapter 17, Least Squares Regression, part 1. So here are the 3 learning goals. At the end of this, you will know why the smallest sum of the squares results in a best fit line to data. You'll understand the derivation of the equations for the least squares regression coefficients, and you'll be able to quantify the error of a least squares regression fit. So let's just kind of discuss the theory of least squares. How do you accomplish this? And first of all, what our ultimate goal here is we have a series of measurements or a series of data. This is really core to engineering. And what we would like to do is this looks like this is some sort of linear relationship, and we'd like an equation for the line of that best fit. Clearly there's some experimental error going on here, but we're trying to figure out what would be the best fit line that goes through there. So there's what our ultimate goal is. And so we want this also to be a unique line, a single line that is the best fit and has a unique solution to it. And there's a couple different ways that you could quantify the error. So I'm going to go ahead and review these. These are also discussed in the textbook to arrive at why we use what we do, which is the least squares. So first of all, you might have what would be our traditional type of error, which is what we're going to do is just take the measurement between the value that we have, our experimental value, which is y sub I, and then we're going to go ahead and just subtract where it is from the line. So effectively what we're looking at is that distance right there. So this right over here is, for example, the data point. This dashed line over here would be our best fit, and so this would be a measurement of our error. And that's kind of typically what we do when we quantify error. We just look at the difference between the numerical prediction and the actual prediction. Well, and then if we were to sum that over all of our data points, well, this wouldn't be a good measurement because what we'd have is sometimes that might be a positive error and sometimes that might be a negative error. Those would cancel out. And so therefore, this dashed line that I show right over here would have a best fit line, or essentially an error of 0, because they would balance out themselves exactly. When clearly I want the solid line right over here where the error would be 0 going exactly through the points. So this one right over here is not a good idea. All right. Now, one thing we could do to go ahead and get rid of the positive and negative effects is just take the absolute value. And again, that's something we typically do when we look at errors. The problem with that is that now we're going to end up having not a unique solution, because either of these two dashed lines would end up with the same result. And in fact, it turns out any value in between there, any dashed line in between it, would end up with the same value of line. So then it would not be a unique line. We want a unique line, clearly, to have the description of this data. So this is not a good idea either. Another possible idea is just to say, well, I'm going to go ahead and get a line that seems to minimize what the discrepancy is between the data points and the line. And so this is called, it's called the minimax. I'm going to minimize the maximum distance. So I'm going to go ahead and find a line that's going to go ahead and minimize the maximum distance between this line and my data points. Well, what this does is this gives too much weight to this single outlier. So clearly I don't want to go ahead and do that, because one bad data point really skews my line. So to address all those points, what we do end up doing is we take the error like we had in our first example, and we go ahead and square it and add up all of those. And so by squaring it, what we end up doing is now we get rid of the positive negative problems. Also, by squaring it, what it does is at the further the line becomes a discrepancy from the points, it grows much faster, so we get rid of this non-uniqueness of the solution. And because we're summing up all of these values, this is going to give weight to values that occur on the line, which the minimax problem had. So now we've got a good description of what our error would be. We're going to go ahead and sum up all of this differences and square it each time. Okay, so how do we determine what the coefficient values are? So what we have is our best fit line we want to have is y is equal to a1x plus a0. So we have a 2-parameter polynomial. And what we're doing is we're trying to find that equation of that line that goes right through here. So a0 is our intercept, and a1 is our slope of our line. And we're just looking for a single line. We'll look at higher order polynomials in a later video. And what we're doing each time is we're looking at the differences between the point and where it would be on the predicted line, and then we're taking that area of it. So effectively what we're doing is we're squaring it and adding up all that. And that's what this parameter s sub r is. And so we're minimizing this value in order to find that unique line. And so if we want to minimize it, what we end up doing is we're going to take the derivative and set that equal to 0. And now we've got two parameters, a0 and a1. And so in order to find both of those, we do partial derivatives. So first we take the partial derivative of SR with a0. set that equal to 0. That's going to give us one equation. And then we've got the partial derivative with respect to a1, set that equal to 0. Two equations and two unknowns. So these are my two equations. My unknowns are a0 and a1, and I'm going to go ahead and solve this. And there's a lot of algebra in here, particularly a lot of algebra involving summations, which you may or may not be comfortable with. That's okay. As long as you recognize where these equations come from. Here's what the equations are. You'll never have to manually type this in. Almost any calculator can actually calculate these for you, in addition to most numerical packages like MATLAB, which we'll look at in a later video. But here's what the coefficient values are. This is a1. This is what the slope is. There's a lot of different summations in here, and this is why you tend not to ever really want to do this by hand. But really easy to do in loops on a program. As I said, almost any calculator these days can go ahead and give you these parameters as well. So, and then here's for the intercept a0, where this over bar is the mean value or the average value. So this is what the over bar means. So we've got our average value of y and our average value of x. This one's a little simpler to do, but first you've got to calculate your slope, which is your a1 value, because that goes into there. So this is kind of a1 value is calculated before the a0 value. All right. So now we know how to find our parameters a0 and a1. The next thing we'd like to know is, well, how well does that line fit the data? What is the magnitude of SR mean? And so the way that this is defined now, because remember it's the summation of all those squares, the more data points that you have, the higher SR is going to be. Simply, you're just going to have more data points farther from the line. Just because you have more data points doesn't mean that your error is necessarily larger. So we need some way to go ahead and more or less normalize SR. We'd like something that's on the order of something between 0 and 1. Again, typically our errors are some normalized value. You can say between 0 and 1 or 0 and 100%. So we'd like some way to quantify SR into this range. We need to normalize it by something that's on the order of the magnitude of that. So one thing we can do is we're going to go ahead and use just what would be the average discrepancy. So here's what the idea is. So this value of SR right over here, S sub R, remember what we're doing is we're taking the sum of all these distances of our data points from our line and adding them up. And so this kind of gives us a feel for what the spread is in the data, which is kind of what this diagram is showing here. Alternatively, if I had all this data and we didn't assume that it was a correlation, for example, it was just they should have all been the exact same value, right? They should have all been this value here, and this was just experimental error as I moved across. I would go ahead and have a summation of all these square values here. That would clearly be much larger. You can kind of tell from looking at this line. This value is always going to be much, much larger than this one. But they're going to be on the same order of magnitude. So this is actually a good metric to go ahead and use this value. And this is called S sub t. Where now I'm just squaring the difference between the mean value, not the value predicted by the line. So that would be the mean value. This right over here is the equation of my line. And so I'm going to be subtracting out a number that tends to be further apart from the data points. And now I can go ahead and have some sort of metric. So I'm going to normalize those by S of t. So really what I'm going to do is I'm going to define this parameter called r squared, which is the value of S of t, subtract SR, and then normalize it by ST. So I'm going to have something on the order of 1, something between 0 and 1. And so now I go ahead and just plug in this equation for ST, this one for SR, go ahead and calculate what the R value is going to be. It gets pretty complicated in terms of algebra. Again, you'll never have to type this in by hand. All your calculators will always give this to you, or numerical packages. But again, it's good to recognize what it represents. So this is what it represents qualitatively. Here's what the value of R is. Again, it involves all of these tons of summations. And the value of R tends to be called the correlation coefficient. So you'll often see when someone presents some data and they're claiming that it has a linear relationship, they'll give you a value of the correlation coefficient. So let's look at what the values of the correlation coefficient could be. Well, if R squared was equal to 1, all right, if we look over here, if R squared was equal to 1, what that means is that S sub R would be equal to 0. So that means, if we look over on our diagram over here on the right, if that was equal to 0, that means that the line went through all the data points. All the data points fell exactly on the line. So it was a perfect fit. So R squared equals 1 is a perfect fit. Now the lower end value could be, we could have an R squared of 0. And R squared is 0. If I look at what would require for R squared to equal 0, that would say S sub R is equal to S sub t. And what that tells me is that there was no correlation at all. I ended up with a similar spread, just like it was an average value. So that would essentially mean that there's no correlation between the data. It's really just like making the same measurement, and any variance I have is just experimental error. You can have r-squareds that are less than 1. That would be, so, for example, some line that goes in this direction. You'd never have a line that's going in the opposite trend necessarily. So normally we just look at that, assume our values of r-squared are between 0 and 1, going from no correlation to a perfect correlation. So one of the last things I just kind of want to mention here is you want to be careful, though, when people give you a value of r-squared. You'll often see maybe a presentation where someone presents some data, and then they go and say, hey, my r-squared value for this is blah, blah, blah. And so usually what you see is a lot of heads just kind of bob and say, okay, that's great, and you believe that it's good. So here's kind of a quick thing to kind of quantify how, well, what's your gut feeling for r-squared? Here I have 3 plots of data, all right, and then I've got 6 options for r-squared values. So go ahead and pause the video and think for a minute and try to guess which one of these plots represent which one of these r-squared values. Okay, well, I'll go ahead and give you the answers. This one on the upper hand left, this is A. Our r-squared value is 0.995. So even though you see some variability in that, it's actually a very, very good fit. And so that will give you an r-squared value of 0.995. We see a little larger discrepancy over here on the right. Well, that one right there is actually B. So again, we have a value of 0.97. So what this tells you is that I see a little more variation on the right than the left. Tends to be if someone tells you it's 0.995 or 0.97, those both sound like really, really large values. And so it kind of tends to be true. Now let's look at the one on the lower left here. We clearly see some more outliers on this one. So what would this r-squared value be? Well, this one is still pretty high. It's actually 0.92. This one right over here is C. And so although now we're starting to see some larger variability, we're still getting a correlation coefficient that is greater than 0.9. So really, you have some really bad correlations once you get below 0.9. And so if you ever see an r-squared value that's less than 0.9, say 0.85, it's probably not actually a very good fit. But it's really tough to kind of see that number and have some idea how well the data fits. And as well, what you can see is these third digits over here are sort of meaningless. And sometimes you'll see people go ahead and report an r-squared value to like 5 significant figures, where those last few significant figures are more or less meaningless. They really don't give you any sort of information about how well it fits. Okay, let's just go ahead and review this video. First we saw is that there is a unique best fit line to data, and you can determine it by minimizing the total square error in each of the data points. You're going to go ahead and find the 2 parameters, and they're determined by setting the partial derivatives of this total square error to 0 and solving for A0 and A1. The error in the data to line agreement can be quantified using a value called r-squared, and it's the ratio of the linear error, the error between the line and the data, to the average value data. So if you just said that there was no correlation at all. And that's going to go ahead and give us a value between 0 and 1. And finally, as I just mentioned, r-squared 1 is a perfect fit, and r-squared equals 0 indicates that there is no correlation at all.